Early atomic theory evolved over time as scientists developed new ideas about the nature of matter. The concept of atoms dates back to the Greek philosopher Democritus in the 5th century BCE, who proposed that all matter is composed of small indivisible particles called atoms. However, his ideas more purely philosophical and lack of experimental evidence. In the early 19th century, English chemist John Dalton revived the atomic theory with a scientist approach suggesting that matter is made up of atoms, which are indivisible and combine in a simple ratios to form compounds. Dalton's theory was based on experimental evidence, especially in chemical reaction, and laid the foundation for modern chemistry. In 1897, G. G. Thomson, through experiments with cathode rays, discovered the electron and proposed the Planck pudding. Models where atoms consistent of a positively charged pudding with electrons embedded within it. Later in 1911, Ernest Rutherford gold foil experiment revealed that atoms share mostly empty space, with a small, dense, positively charged nucleus at the center, leading to the rejection of the Planck pudding model and the development of the nuclear model of the atom. These early theories gradually build the foundation for our current understanding of atomic structure.
Welcome everyone. Today's discussion focuses on historical development of atomic theory, tracing its journey from alchemy to the modern understanding of atoms. We'll explore key figures, experiments, and the evolution of scientific thought. The evolution of atomic theory from alchemy to modern science. First, alchemy and early chemistry. Islamic alchemists like Habir ibn Hayyan emphasized experimentation, leading to advancement in distillation and metallurgy. Though alchemy mixed science with mysticism, it laid the groundwork for modern chemistry. Boyle's experiment and atomism. Robert Boyle showed that air is compressible, suggesting it's made of tiny particles. His findings helped shift the view of matter from philosophy to experimental science. Lavoisier and the conservation of mass. Lavoisier proved that mass is conserved in chemical reactions. His precise measurement and discovery of oxygen's role in combustion shaped modern chemistry. The evolution of atomic theory. Lavoisier proved that mass remains constant in chemical reactions, meaning matter isn't created or destroyed, only transformed. Prost's law of definite proportions. Prost showed that compounds always contain elements and fixed ratios by mass, supporting the ideas combined in specific ways. Dalton's atomic theory. Dalton proposed that all matter is made of invisible atoms, which combine in whole number ratios. However, he didn't know about subatomic particles or isotopes. Thomson's plum pudding model. Thomson discovered electrons providing atoms are divisible. He proposed that atoms are positively charged spheres with electrons embedded inside, challenging Dalton's model. Thomson's cathode ray tube experiments and the discovery of the electrons. The cathode ray tube, or CRT. A CRT is a vacuum tube with a cathode or negative and anode is positive. When voltage is applied, cathode rays travel from the cathode to the anode, producing a glow on the screen. Thomson's experiments and observations. He applied electric and magnetic fields and observed that the rays were deflected, proving they carried a negative charge. The deflection was the same for different cathode materials, meaning these particles were present in all matter. Charge to mass ratio calculation. Thomson measured how much the rays bent in the field, calculating the charge to mass ratio. This ratio was much higher than any known ion, proving the particles were extremely small and light. Discovery of the electron. Thomson concluded that cathode rays were made of negatively charged particles electrons. J. Thomson's plum pudding model. Thomson's experiment proved atoms contains negatively charged electrons, meaning atoms weren't indivisible. Since atoms are neutral, there had to be positive charge to balance the electrons. The plum pudding model. Thomson proposed that atoms are spheres of positive charge pudding with electrons embedded inside plum. Strength and limitations. Strength, first model to include subatomic particles. Limitation. Rutherford's gold foil experiment later proved that atoms have a dense nucleus contradicting Thomson's model.
Rutherford's model of the atom. Ernest Rutherford tested Thomson's plum pudding model by conducting the gold foil experiment, where he bombarded a thin gold foil with a high velocity alpha particles. According to Thomson's model, the atom mass should be evenly distributed, causing only minor deflections. However, Rutherford observed that most alpha particles pass through the foil, suggesting that atoms are mostly empty space. Some particles were deflected at angles, and a few even bounced back, leading him to conclude that the atom has a small, dense, positively charged nucleus at its center, disproving the plum pudding model. Here is a simplified diagram of Rutherford's gold foil experiment. It clearly illustrates the key concepts: the alpha particles, gold foil, deflected particles, and the nucleus. Eugene Goldstein used a gas discharge tube with a perforated cathode and observed positive rays traveling from the anode to cathode. He proposed the existence of positively charged particles to balance electrons. However, he found that the mass-to-charge ratio varied with different gases, leading him to conclude that these rays were ions of different fundamental particle. Bohr's model of the atom. Niels Bohr resolved a flaw in Rutherford's atomic model by proposing that electrons move in fixed energy levels without losing energy. They can only gain or lose energy by jumping between levels, explaining hydrogen's emission spectrum. His model introduced quantum theory to atomic structure and laid the foundation for modern atomic physics. The observed colors emitted by a hydrogen atom are violet, blue, green, and red. Since the color red is the most intense, the observed color of light emitted by hydrogen atom is red. Although Bohr atomic model only applies to the hydrogen atom, his work was considered valuable. He was awarded the Nobel Prize for Physics in 1922. Nuclear model of the atom. What are the major components protons, neutrons, and electrons. Rutherford discovered the positively charged nucleus containing protons, while Bohr proposed that electrons occupy specific orbits around it. However, the total atomic mass remained unexplained until Chadwick discovered the neutron in 1932, confirming that the nucleus consists of both protons and neutrons, while electrons move in the surrounding space.
Lesson 3 Subatomic particle and nuclear reaction. Subatomic particles are the fundamental building blocks of matter, and they include protons, neutrons, and electrons. Protons are positively charged and reside in the nucleus of an atom, determining an element's density, while neutrons, which have no charge, also exist in the nucleus and help stabilize it. Electrons, negatively charged, orbit and nucleus in various energy levels and 1K to chemical bonding and reaction. Nuclear reaction, which occur within and nuclear reaction, which occur within and nuclear, involves charges that release large amount of energy. There are two main types. Nuclear fusion, uranium and plutonium, splits into smaller nuclei, releasing energy and often initiating a chain reaction. And nuclear fusion, where large atomic nuclei like hydrogen combine to form a heavier nuclear, also releasing vast energy. While fusion which used a nuclear power plants and weapon fusion where star like the sun, both processes are driven by the strong nuclear force which burns protons and neutrons together with fusion, offering the potential for a nuclear energy source, though achieving it on Earth remains challenging due to the extreme condition required.